right, so this is just going to be a quick video going over some of the polynomial application problems that we are covering in this unit. So the first two problems are very similar in that they are giving you the equation. They don't come right out and give you the equation in number one, but they give you the format for the equation, and they tell you that it is 40 feet above sea level and there's an initial velocity of 65 feet per second. So h sub 1 is the initial height and v sub 1 is the initial velocity. So therefore, I know that the equation is d equals negative 16t squared plus 65t plus 40. So this situation is we're trying to figure out if a flare that is fired from a certain point is visible from somewhere else. And it says for this flare to be seen on the eastern shore, it would have to go at least 150 feet in the air. So we're trying to figure out if this particular flare that is fired from this particular place goes high enough for somebody on the eastern shore to see. So we're going to go to our calculator, go to y equals. We're just going to type this in. Obviously, we have to type it in terms of x and y instead of d and t. So it's going to be negative 16x squared plus 65x plus 40. The window is really important. If I'm trying to find the maximum, I need to see that on my graph so that the calculator can tell me where it is. I can look at this equation. I can see that it's second degree, it's even and negative, so it opens parabola that opens down on both ends. So that's what I should expect to see. So if you go to your window, I'm going to a zoom 6 window. Zoom 6 is a standard window, negative 10 to 10. So you can always start with that. You can also try zoom fit, which is zoom 10, but zoom 0. But the main thing is we need to know what that maximum is. So I'm going to go back to zoom 6. I know right off the bat, I'm trying to see if this flare goes 150 feet in the air. So how high something goes would be represented by y max. So I know that I'm looking for at least 150 feet in the air, so I'm just going to overshoot that just a bit and change it to 155. And I'm going to hit graph. Okay, so as long as I can see the maximum, that's what I need. So on my paper, I'm just going to do a quick sketch of the situation, and I am looking for this point right here. So I'm doing second, trace, maximum. It asks for a point to the left of the turn, hit enter, a point to the right of the turn, hit enter. It says guess, just hit enter. Okay, so then I'm going to write down that maximum point, 2.031, comma 106.016, 3 decimal places. So how that translates to the context of this problem, since when I put this in the calculator, it was representing this equation, then the x-coordinate must represent t, or time, in seconds, and the y-coordinate must be distance, or height, in feet. So this means that at 2.13 seconds after it's fired, it reaches a height of 106 approximately feet, cutting off the decimal there. So remember, this asked, it said that it needed height of, it needed to reach 150 feet. This reaches 106 feet. So will it be seen? No, because it only goes 106 feet. So problem 2 is really the same thing. It's even easier because they gave you the equation. So again, you're just going to go to y equals, type it in, adjust your window. So just do that really quickly. Clear that out. So type in 80 plus 72x minus 16x squared. I'm just going to see if the last window I used was good. I can always adjust it. So I'm just going to go ahead and hit graph. Okay, so it's almost. I just have to raise the y max just a little to see that turn. So I don't have any magic formula for punching in the right number. I'm just taking a stab at it. Okay, so as long as I can see that turn. So I would make a sketch, I would find that maximum, I would write it down, and based on this problem, the ball was thrown vertically upward from the top of an 80-foot tower with an initial speed of 70 feet per second. So when I find the maximum, then the x-coordinate will be time and the y-coordinate will be the height. So I will just look at that maximum ordered pair, and the y-coordinate will give me the height reached by the ball, and the x-coordinate would be at what point after it's thrown that happens. All right, so now we have perimeter area problems. So I would always suggest sketching a picture. You should know the formula for area and perimeter of a rectangle. So it says there is a rectangular pin in the backyard, and it's going to use the back fence as one of its sides. You can only afford to purchase 60 feet of fencing. Fencing is always about perimeter. If you buy fence panels, you place them around the perimeter of the area you want to fence in. So if I can have 60 feet of fencing, then that means that my perimeter can be 60 feet. And this rectangle, you have the width and you have the length. Normally I have 4 sides, but since I'm using an existing fence as one of my sides, then I'm only going to have 3 sides involved. So the perimeter of a rectangle is 2 times the width plus 2 times the length, but since I am only using this one side, it's just going to be plus 1 because there's only 3 sides involved in this situation. And I was told that I have 60 feet of fencing, so I know that the perimeter is going to be 60. Okay, but what I'm trying to maximize or minimize is what has to go in the calculator. And I'm supposed to be finding the dimensions of the pin that will allow the greatest area. So I am trying to maximize my area. And the area of a rectangle is length times width. Doesn't matter that I'm using one side that's already there. But this has to go in the calculator because that's what I want to maximize, but I can't type this in the calculator the way it is because when I type an equation in the calculator to graph it, I've only got 2 variables, x and y, and this has a total of 3 variables. So I'm going to go back over here where they gave me some more information, and I'm going to solve this equation for L by subtracting 2W. This creates a substitution, similar to when you solve a system by substitution. So I can come back over here and I can replace this L with 60 minus 2W. Now I only have 2 variables, so I can put this in my calculator. If you want to distribute, you can, but the calculator doesn't care. It's the same equation either way. So I am going to go to y equals. I am going to type in my equation, which is 60 minus 2W. That'll be 2x. And times x. I'm going to put it in parentheses. I don't think you really need to. All right, just going to see if my last window is good. Can always adjust it. All right, looking at this polynomial, if I were to distribute, it is just like the others. It's a parabola that turns down. So looking at this view, I need to see further to the right and I need to see further up. So I need to adjust my x max and my y max. I usually just double it and see if that's good enough. So I'm going to just do 400 here. It's easier math. See if that works. All right, no, I still need to see higher and further to the right. So I'm going to go back. I'm going to, maybe I'll do 50 this time. And I'm going to do 500. Because it didn't look, okay, perfect. I just need to see this maximum. So second trace maximum, point to the left, point to the right, hit enter. So my maximum, I just have a little sketch. It's a parabola. My maximum point is 15, 450. So I put this in my calculator as in terms of x and y, but the x coordinate is representing the width and the y coordinate is representing the area. So 15 is the width and 450 is the area. So find the dimensions that will allow the greatest area. The max area is 450 square feet. And if the width is 15, so I can come up here and if I put 15 in for the width, 2 times 15 is 30. And so together it has to equal 60, so L must be 30. 2 times 15, subtract that, so 30 equals L. So the dimensions would be 15 by 30 feet. All right, so 4 is similar. It's a rectangle. It mentions an area and a perimeter. So it says that the area of this rectangle is 36 centimeters squared. So I know that I have the width on both sides and the length. And I know that the formula for the area of a rectangle is length times width. And I know the area is 36. But what has to go in the calculator is what I am maximizing or minimizing. And this says that I want to minimize the perimeter. So that has to go in the calculator. The perimeter is 2 times the width plus 2 times the length. But again, problem is too many variables to put it in the calculator. So I come over here. I'm going to solve this for one of the variables. Doesn't really matter which one. That's my substitution for over here. And I can put this in the calculator. Now, this has a variable in the denominator. So it's not a parabola. It's a rational function. So you really have to pay attention to your window when working with a rational function. Clear that out. So 2x plus 2 times 36 divided by x. All right, I'm just going to check and see if the window that I had for my last problem, and it's fine. It really doesn't adequately give you a good view of that function, but I just need to find the minimum. And as long as you feel like what you're looking at, you can find the minimum, you're good. So I'm going to go second, trace minimum, that's 3. So watch the x and y at the bottom. See how the y is getting smaller as I move to the left. I'm going to make sure that you watch it go smaller, and then when it starts to go back up, you know you've cleared the minimum. So hit enter. Now for the right bound, I'm going to watch that y value, see how it's going down as I move to the right. When it starts to go back up again, I am on the other side. If you get an error message, it means you pick 2 points to the left or 2 points to the right. So you got to really make sure you're on either side of the point you're trying to find. So if we do a quick sketch, basically this, we're looking for the minimum. The minimum is 6, 24. So in terms of the equation I put in the calculator, the x coordinate is the width and the y coordinate is the perimeter. So the width is 6 centimeters. And if I put that back in here, then the length would also have to be 6 centimeters. And the minimum perimeter is 24. Right there. Okay. Now, let me go back to the calculator for a second. Let's say I did like zoom 6. That's just negative 10 to 10. That's not great. I don't see anything. So obviously that's not a good choice. So let me try that zoom fit. It's actually a great graph for this function. But if you use this window, you can't really determine where the lowest point in this curve is. And so you really want to make sure that you change your window so that you can focus in on the curve in the first quadrant and you're really able to find that lowest point. This would be really tough to find the lowest point with this window for that equation. All right, so we're going to do one more. Both 6 and 7 are talking about creating an open top box. And the way that we do that is you start with rectangle. So it says a rectangular piece of cardboard, and it is 6 by 10 inches. And we are going to cut squares out of each corner. These squares should be the same 4 squares, so the same size, but we don't know what size they should be. So each of these squares we know, since they're going to be the same size, x times x. Okay, so this width was 6 inches, but I cut out 2 squares, so I cut out 2 x's. So now this is 6 minus those 2 x's. And this length was 10, but I also cut out these 2 x's. So now this is 10 minus 2x. And so if you actually take a sheet of paper and cut out squares from each corner, you create these 4 flaps, and then you can fold those flaps up and secure them, and that creates this open top box. And we're trying to maximize the volume. The volume here would be length times width times height. Well, the length was 10, now it's 10 minus 2x. The width was 6, now it's 6 minus 2x. And that x creates those flaps that I'm going to fold up, so the height is x. So I only have one formula. I don't have to make any substitutions. This is what's going to go in my calculator. This is a cubic function. It's negative and it's odd, or so no, it's positive and it's odd, so I know what to expect from the graph. So when I put it in my calculator, 10 minus 2x, 6 minus 2x times x. All right, so I'm gonna try zoom 6, see what I got. Not bad. I'm trying to maximize the volume, so I really need this. I don't need this. So I'm gonna go back to the window and adjust it a little bit. I just need to see higher. I'm gonna make it 20. Usually I double it. Okay, and I need that point right there. Make sure I did not enter. Oh, you know what? I didn't close my parentheses. I knew there was something off. I knew that was. Okay, let me try again. See what my graph looks like now. Okay, that's better. So I need to see higher. If you want to see lower, you're just trying to find the maximum, so that's up to you. So I am going to go, I'll go ahead and double that, and I'm going to double this. I doubled the y max once, but I'm going to do it again. Okay, perfect. I need to see this maximum. Second, trace max, point to the left, point to the right. And so my sketch be like, and I'm trying to find this point right here. So my maximum is 1.214, comma 32.835. All right, so what that means is when I put this in, X was what I was cutting out and Y is the volume. So the maximum volume is the 32.835 and inches cubed from right here. And I need to figure out what size are these squares I'm going to cut out. That would be from here. So the squares are going to be 1.214 inch by 1.214 inch. So here's my maximum volume. That's the size of the squares that I need to cut out. All right, so 7 is just another problem like this, just a little bit different numbers. That's what we got through in class. And it won't be on the quiz next class, but it will be on the upcoming test.